We're going to resume our discussion here with Chapter 5, but picking up on Section 5.3 and 5.4, which is on page 9 of your Chapter 5 notes. And it's kind of exciting. We're actually a few weeks into the class now. Exciting music there. That's good. A few weeks into the class now, we're actually going to get started talking about statistics. So far, we've talked about a lot of probability and random variables, expected values, all that kind of stuff. Now we're actually going to finally get into some statistical methods, which we're getting into the good part of the course. So sort of as a motivating example here to get us thinking about what we're going to do in this section, kind of a usual setup that we've seen before. Suppose that the amount of time a randomly selected commuter spends traveling to work follows an exponential distribution with parameter lambda of 0.05. If we let x equal the amount of time that this commuter spends traveling, then we might let x be distributed as a exponential random variable with parameter 0.05. And then you could answer a number of questions. There's a question very sort of like this in your homework. What's the probability that the commuter spends more than 20 minutes going to work, or something like that, or something like this. Yes. So when back in that setting, we were asking questions. We were asking what might happen if this commuter walks out the door one day and goes to work. So we're asking questions about what could happen. What could happen or what might happen here. And again, this is kind of a specific example of an experiment. So what might happen if we do this experiment one time? So the question that we're asking here is, suppose we do this experiment one time, or suppose this person drives to work, and we're going to see how long that takes them. What's the probability that it takes them more than 30 minutes to get to work, or something like that. So the key is we're asking something about doing this experiment one time. But you could think about what if we were to independently repeat this experiment some arbitrary number of times n. So suppose we were to repeat this thing n times. Each one is independent from the others. So before we do this experiment, before we do this n times, we have here's some new terminology. We have n independent and identically distributed random variables. So x1 is from the first experiment, maybe from the first day that this person drives to work. X2 is maybe the second experiment, all the way up to the nth time we do this. So our notation here, and we'll use this abbreviation here, IID, to represent independent and identically distributed. So our notation is going to be, we'll have x1, x2, all the way up to xn. Our IID, and for example, in the previous example, their IID exponential with parameter 0.05. So again, this here means independent and identically distributed. So independent as in the random variables are all independent of each other, and identically distributed, they have the same distribution. So that'll be our shorthand notation for that. But the point is here that before we do this experiment, we have a bunch of random variables, right? These are all random variables. On any particular day, we don't know how long it'll take this person to get to work, but we're going to say that it follows this distribution, this exponential distribution. Okay, so then say we actually go ahead and do this experiment. This person drives to work n days or something like that. So after those experiments are performed, we have data. We have a sample of size n. So Our notation here will go from capital letters being random variable to lowercase letters. This is observed. This is observed data. And these will all be numbers. So first day maybe it took him 22 minutes to get to class. Maybe the second day it took him 18 minutes to get to class or get to work, and so on. So after we perform an experiment, we've done this thing n times, and we have information on each one of those trials. So again, we'll follow that convention that we've used before of capital letters are a random variable, lowercase letters are some observed value of that random variable. So here, while the word statistics is sort of in general used to talk about a academic discipline, the discipline of statistics, the word statistic actually has a very specific meaning that we can use in this class. So here's our definition. First sentence there. A statistic is any quantity whose value can be calculated from sample data. So I have a bunch of information. I have maybe n numbers. A statistic is just anything I can calculate from that. So we'll look at some examples of that. But the point is that I can calculate this thing from the sample data. So prior to collecting the data, like we saw just before, I don't know what my data is going to be, right? So the statistic itself I'll be uncertain as to what that thing might be. And again, we'll use, so therefore a statistic is a random variable itself. So you could think it's a function of a bunch of random variables. I don't know what that's going to be, so it's a random variable as well. And so we'll use an uppercase letter to denote a statistic. And when we have a lowercase value, again, that'll be the calculated or observed value of the statistic. Okay, so for example here, let's say, so before I observe the data, I have this collection of random variables, x1 up to xn. I could some statistics I could calculate here would be something like I could do the sample mean, which is again just the average, 1 over n times the sum. I could calculate sample mean. I could calculate the minimum, which would maybe be call that thing n, which is the minimum. Any other ideas of what I could calculate here as a statistic? There's not just one answer.
You can calculate the maximum.
I calculate the maximum, absolutely, yeah. I could calculate the median. I could calculate the mode. I could calculate anything really. So the point is just something that I'm interested from this collection of numbers, something I can actually calculate from that thing. So anyway, after I observe the data, then I can actually plug in numbers and figure out what this is. So my sample mean will now use a lowercase x, which is the sum of all the observed x values. This is my observed sample mean. And maybe a lowercase m is the minimum of all the observed values. It's my observed sample minimum, and so on. So the exact example, the specific statistic here isn't the point. It's just that we'll try to use capital letters to denote sort of an unknown random variable, and we'll use lowercase letters to denote an observed value of those things. Is the notation okay? You guys with me so far? Okay. Well, two statistics that we'll see in general, and one we've already looked at here. And I'll put formulas up for these things again, but sort of the two most common ones that we'll use are the sample mean which is again what I've written before, and also the sample variance. So you can imagine that thing is sort of like the we have some xi minus something squared. It's kind of like an idea similar to the variance that we've seen before. I'll say more about this later, but I just mainly wanted to point out this notation. We're going to use x bar to denote the sample mean. So it's a common thing in statistics to use some sort of bar or a hat or something on top of the letter to represent particular things. So you'll see a lot more of that. But x bar is going to be our generic notation for the sample mean, which is just the average, the usual average there. Okay, so that's just some notation. But again, kind of coming back to this idea, before I collect the data, this statistic, whatever it is that I'm looking at, is a random variable, right? So before my experiment, I have no idea what the xi's are going to be, x1 up to xn, and so I have no idea what the sample mean is going to be. So that's a random variable, and kind of going with what we've seen before, a random variable has a probability distribution, right? Either a probability mass function or a probability density function. And our special name for these probability distributions of statistics is a sampling distribution. So a sampling distribution. And again, this sampling distribution is going to describe the behavior of my statistic. So the sampling distribution again describes the distribution of my statistic, or think about sort of how that well, I'll just write that down. Describes the distribution of the statistic of interest, so whatever that might be. And yeah, and that's going to describe sort of the behavior of how this thing over all possible samples that might be collected. So if I take one sample of 10 people, I'm going to get a certain sample mean. If I take another sample of 10 people, I'll get a different sample mean, and so on like that. So there's a bunch of different possible samples that I could collect, and so this is going to describe sort of how that statistic behaves over all those possible samples. So sort of some assumptions that we're going to make when we're looking at these things. These are assumptions that sort of allow us to calculate these things. Is the setup as given here. So I have x1, x2 all the way up to xn random variables, and we're going to say that they form a simple random sample or just a random sample if two things hold: if they're all independent and if they all have the same probability distribution. So this might kind of sound like the IID thing that we saw before. So whenever you see the word random, when you see the phrase random sample, that's going to mean something very specific, which is right here. We're going to say that those things are independent and they all have the same distribution, or their IID. So if you see random sample, that means this here. And so in some cases we can, for some sort of simple cases, we can derive the sampling distribution from a random sample like this, and in other cases we might need to rely on some computer simulation to get a kind of approximation of what that thing will be. Okay, so enough definitions here. Let's try to do an example here. So suppose that I flip a coin 3 times, and the coin is weighted such that the probability of landing on heads is 0.6. So it's an unfair coin here. And let's let xi equal 1 if the coin lands on heads on the ith toss, and 0 for tails. And we want to find the sampling distribution of x bar. So it's kind of implicitly assumed here this is coin tosses are independent. So I'm going to flip this coin. The result of each coin toss doesn't affect the other ones. The coin doesn't know what it just did. So, and have independent there, and then I'm using the same coin, so they all have the same distribution. So, and identically distributed. So I have the same coin. It's going to have the same probability of landing on a head each time. Okay, so I have 3 coin tosses. So I have x1, x2, and x3. And what is the distribution of each one of those coin tosses? So x1, what's the distribution of x1? Remember back to chapter 3. So just x1. What's the distribution of just one of those things? So I can either get a 1 or a 0, right? I have 2 outcomes and I have just one thing. Do you guys remember what that's called? I think, did I see it? Bernoulli. Yes, exactly right. So these are Bernoulli random variables, again with success probability 0.6. So success probability here means the probability that I get a 1. Okay. So then I'm interested in the sampling distribution of x bar. So we need to figure out what possible values x bar can take on, and then the probability of each of those possible values. So what are the possible values of x bar, which is the sum of those three coin tosses, the average of those 3 coin tosses? What are the possible values of x bar here? Give you a hint, there are 4 possible values. So what happens if all the coins are tails? So if I get 0, 1, 2, and 3 that would be possibilities for this part. If I'm taking the average of the sum, yeah, right. So the sum can either be 0, 1, 2, or 3, but then if I'm dividing that by 3, it can either be 0, 1/3, 2/3, or 1. So I can get a 0, I can get 1/3, I can get 2/3, or I can get all 3 of those things be heads, in which case the average is 1. Does everyone see where we're getting that? Is that okay? Okay. So again, I want the sampling distribution of x bar. That tells me the distribution of the sample mean. So here's our possible values. Now we just need to figure out what the probability of each of those values is. So let's think about first the probability that the sample mean is 0. Well, that's just the probability that I got 3 tails, right? So if the sample mean is 0, that means first, second, and third toss were all tails. So that's the probability of getting all 3 tails. And these coin tosses are independent, right? So I can just multiply individual probabilities together. This is by independence. And then what's the probability of getting a tail on any particular coin toss? 0.4, thank you. And I can raise that to the third power, which is 0.064. Okay, so for my sample mean to be 0, I have to get all 3 tails, which this would start sort of feeling familiar now to what we've done before. But I have independent coin tosses, I can multiply probabilities together and so forth. Okay, the probability that the sample mean is 1/3. Well, again, that's probably that I get exactly one head of 3 tosses. So what does that sound like? Probably that I get exactly one success out of 3 trials, 3 independent trials. So if I have 3 trials, they're all independent, they all have the same success probability, and I want to know the probability of getting exactly 1 head or 1 success out of those 3 trials. Binomial, thank you very much, yes. So this is going to be a binomial probability. I have 3 coin tosses. I want one of them to be a head. I need one of them to have be a head with probability 0.6, and the other 2, 1 minus 0.6 to the 3 minus 1, which is 0.288. Very good. So this starts to become a binomial type of a situation because I have a fixed number of independent trials that all have the same probability of success. Okay, so similarly, and just to note, we could have done that. We could have done that for the first part too. This is also equal to 3 choose 0 times 0.6 to the 0 times 0.4 to the 3 minus 0. So that will give you the same thing up there. Sort of we can see now that this is the sample mean is going to follow a binomial distribution. Okay, so the probability, that's the first 2 values. Probability that x bar is 2/3. Well, this is also going to be a binomial thing, so this is probably that I have 2 of 3 tosses as a head. So same type of setup, 3 trials, they're all independent, all the same success probability. I want to know probably that I get 2 of 3 as heads, so I have 3 tosses. I want to choose 2 of them to be heads. Then I have 0.6 squared times 1 minus 0.6 just to the first power, and that is 0.4432. Okay, and moving a little more quickly now, the probability that x bar equals 1, the probability that I have all heads, kind of like the first one, and that is similarly binomial probability. And that will give you 0.216. So again, the probability that my sample mean equals 1, I just need to get all 3 heads, and that happens with probability 0.6 to the 3rd power. Okay. So let me jump back in the previous slide to summarize this thing. So my sampling distribution for x bar, I can write down what the probability mass function is. So the observed sample mean can either be 0, 1/3, 2/3, or 1. And then the probability of each of those values is, summarize what we had on the next slide, 0.064, 0.288, 0.432, and 0.216. So here, sort of in this very simple case, I can write down exactly what the sampling distribution is for the sample mean of these 3 Bernoulli coin flip trials here. And again, we could double check that this is a valid distribution, valid probability mass function. All the probabilities are bigger than or equal to 0, and they should add up to 1 if you double check that. So we're in good shape there. Okay, so again, very, very simple example, but just kind of motivate what the sampling distribution is. It's the distribution of the statistic is kind of the main point here. Okay, another example here. So suppose we have, like in the commuter examples here. So on this person's route to work, they go through 2 traffic lights. So let's let x1 be the number of lights that they need to stop at on the way to work, and x2 be the number of lights that they need to stop at on the way home from work. And we're going to suppose that these 2 random variables are independent. You can maybe make an argument otherwise, but let's assume that they are. And they each have probability mass function here. So the number of stoplights that this guy can stop at is either 0, 1, or 2. You could stop at 0, make it through both, or we might have to stop at both of them. And I have 2 of these things, so now I have a random sample of size 2. And again, remember, random sample here. This means independent and identically distributed. Just keep that at the front of your brain. Okay, so that's the distribution of my individual observations here, or individual experiments. And we could ask a question like, what is the probability mass function of t, which is the sum of x1 and x2? So similar to before, the possible values for t are what? What are my possible values of t? 0 through 4, exactly right. So he could, we're looking at the total number of lights that he has to stop at on his way to and from work. That could be anywhere from 0 to 4. Okay, so now, similar to before, we can figure out the probability of each of these possible values. So the probability that t equals 0, well, that's the probability that x1 equals 0 and x2 equals 0. Right? For the whole sum to be equal to 0, I need both of the individual things to be 0. Again, these things are independent, so I can separate these apart. This is the probability that x1 equals 0 times the probability that x2 equals 0. This is by independence. Looking back at the PMF, that's just 0.2 times 0.2, which is 0.04. Okay. So what about for probably that their sum equals 1? Well, I either need for the sum to be equal to 1, I either need the first one to be 0 and the second one to be 1, or vice versa. The first one to be 1 and the second one 0. So it's the probability that x1 equals 1 and x2 equals 0, or so I can add the probability that x1 equals 0 and x2 equals 1. So again, I can split those individual probabilities apart and multiply because they're independent. So this would be x1 of equal 1 is probability 0.5, x2 equals 0 has probability 0.2, and I can add the same thing on there. And that should be 0.2. Okay, let's keep moving along here. The probability that the sum is 2. So there's a few different cases here, right? So we'll start shortening this a little bit. This is the probability that either they're both equal to 1, right? That'll give me a sum of 2. They're both 1, or one is 0 and the other is 2. And I think that's the only ways that we can get a sum of 2. Okay, so the probability that they're both equal to 1, that's just 0.5 times 0.5. That's the probability that x1 equals 1 and x2 equals 1. Then we need to add on the chance that one of them is 0 and the other one is 2. So that can happen in one of two ways, with probability 0.2 times 0.3. Again, I'm multiplying that by 2 because it could be either one. I could have two different orders there. I could have x1 equals 0, x2 equals 2, or x1 equals 2, x2 equals 0. And that has probability, multiplying all those together, that's 0.37. Okay, the probability that the sum is 3. Well, now I need. How do I get a sum of 3 here? Yes, so I need one of them to be 2 and the other one to be 1, but again, that can happen either way. So that's 2 times 0.5 times 0.3. You guys are getting the picture. And finally, the probability that this thing equals to 4. Now I need them both to be equal to 2. So that's the probability that x1 equals 2 times the probability that x2 equals 2, which is 0.3 times 0.3 is 0.09. Okay, so I'm not going to write it out any differently than this, but you could make a little table for what the probability mass function is. You can write out your possible values, probability of each one of those things. If you want to double check that they add up to 1, they're all positive. That's all the usual things that we've wanted to see as before. Okay. So now let's, still looking at the sum of these things, but just to recall, of course, we can do the same things that we've done before with random variables, like, for example, calculate the expected value of t. And there are two ways to go about doing this. Let's just make a quick note that the expected value of x1 is the same as the expected value of x2. They have the same distribution, so their expected value is the same. And that is going to be, again, x1 and x2. So x1, for example, can be 0, 1, or 2. So this is just like we've seen before. 0 times the probability that it equals 0 is 0.2. 1 times the probability of getting a 1 is 0.5. And then I can also get a 2 with probability 0.3. So this equals 1.1. Okay, so the first way I could do this, the expected value of t. Well, that's just the expected value of x1 plus x2, right? And what do we know about expectation when it comes to a sum inside there? How can I rewrite that? Yes, exactly. I can separate them, right? I can take the sum outside the expectation and rewrite them as follows. So the expected value of x1 plus the expected value of x2. So that's just 1.1 plus 1.1, or 2.2. Okay, that's the first way I could do this. The second way would be sort of more directly. Since we went about finding the probability mass function of this sum, we could use that as well. So remember, t could be 0, 1, 2, 3, or 4, and we found the probability of each of those results. So the probability that t is 0 had probability 0.04. Probability that t was 1 was 0.2. Probability that t was 2 had probability 0.37, and so on here. So it was 3 with probability 0.3, and is 4 with probability 0.09. And lo and behold, we get the same thing. So here this is using the probability mass function of t. Okay. So sort of very simple examples here. Just kind of remind you that we're looking at sampling distributions here, which is again the distribution of a particular statistic. So before that was the sample mean. Here's we could just look at the sum of these things, and we can kind of answer the same questions as we have seen before. Okay, a little bit more interesting example here. Suppose now that I have x1, x2, x3, x4. So I have a random sample of size 4 that are IID gamma, and the two parameters are 5 and 4 here. Okay, and so the probability density function for each individual thing looks like this. So it has this sort of skewed right shape. It kind of starts big and then tails off as you go off to the right there. This is sort of like a picture we've seen before. Okay, and suppose now that I take 500 samples of size 4. So I have each one of these things has a gamma distribution, so I can just draw 500 samples. So for each one, I have 4 numbers, and then I calculate the sample mean for each one of those samples. So I take 500 samples of size 4. I calculate the mean for each of those, and now I have 500 numbers, which are sample means of those samples. And then I can make a histogram here. So the histogram here. This is a histogram of the 500 sample means that I can get from this thing. And then over top of that, I've laid that red line, which is sort of you could think about that's what the sampling distribution of the mean would be. So if I kept taking more and more samples, the histogram would look more and more like that red line. So this red line here is the sampling distribution of x bar, a sample of the mean of 4 numbers. Okay, so I'm sort of just showing you a visual thing now. It's, again, the individual random variables, the xi's are gamma, so they could take on any number from 0 to infinity, so it's not possible to write down exactly what, you can't do the same calculation that we just did. We can't write out what all the possible sample means are, but through simulation here I can generate some data that kind of gives us an idea of what this thing might look like. So just to put these things next to each other, and I think the scales are the same there. So here on the left side, I have the population distribution. That's the distribution of each xi. This is a gamma 5, 4. And then on the right side there, I have the sampling distribution. That's the picture we just saw. So for x bar, which is the mean of a sample of size 4 from this population distribution. So just sort of qualitatively, what do you notice about the shape of these distributions? And that I think they should be on the same scale now. How does the blue line compare to the red line? The blue line on the left compare to the red line on the right? Yeah.
It's more like a normal symmetric curve.
Yes, very good. So the shapes are different, right? They're looking different, and the comment was that the red line is starting to look more like a normal curve. If you maybe extend this out a little further, you can maybe see that. That is an excellent observation. So just the point that I wanted to make here is that the shape is different, right? The shape is changing. So the shape of the sampling distribution is not going to necessarily be the same as the shape of my individual distribution for each of the xi's that I have here. So that's the point of this slide, is that the shape is changing. Okay, and you can see this even more clearly if instead of taking a sample of size 4, I start taking larger samples. So here my sample size is 4. This is n equals 4. That's the same picture as we just saw. But if I instead take samples of size 25 and calculate their sample mean, maybe you can see it more clearly in your notes, but it's starting to look even more sort of symmetric and bell-shaped. And then if I come up here to n equals 50, it's even more so. So the shape continues to change. What else do you notice about these three pictures as I go from left to right? Yeah.
As you increase the sample size, it tends to be one exact number.
Exactly right. So as I increase the sample size, you said it tends to be closer to one exact number, right? So the spread, the amount that this thing is spread out is getting smaller and smaller, right? So as I go from here over, I have less spread. Or you could think about it in sort of more formal terms. We have smaller. I have smaller variance as I go from left to right. So remember, the variance is a measure of how spread out this distribution is. So as it's getting more and more scrunched together, that just tells us that the variance, just sort of looking at it, that the variance is getting smaller. So the two key observations are that the shape is changing and it's getting more and more sort of clustered together. Those are the two main points that I wanted to make here. Okay, so this is an idea that we will revisit shortly, but the picture to keep in mind there. Okay, so when we're talking about random variables in general, when we have a random sample of these things, there are some sort of general properties that we can take advantage of. And again, most often we'll be dealing with the sample mean. That's kind of our favorite thing to look at. And so here's some properties of what that is. So if my x1, x2 up to xn are a random sample from some distribution that has mean, mu, and variance sigma squared, so the expected value of the xi's, they're all the same, right? They have the random sample. They all have the same distribution. They all have the same mean, and the variance. Each one of these things is also all the same. It can be sigma squared. So whatever the distribution is, we can find what its mean and variance is. Then there's two important properties here. So the sampling distribution of the mean, so the sampling distribution will also have mean mu. It's going to have the same mean, but its variance is going to be different. So these are properties of the sampling distribution. So it's going to have the same mean, but its variance is going to be different. So mean of x bar is still mu, and the variance now is going to be slightly different. It's going to be sigma squared. I'm going to divide by the sample size. So sigma squared over n is the new variance of this thing. And standard deviation is the square root of that, sigma over the square root of n. So that kind of maybe this is some formally backs up that picture that we saw previously. When my sample size gets bigger, my variance is going to get smaller. So the distribution is getting more and more sort of clustered around a single point there. And then if we happen to be talking about just the sum, which we'll use a capital T, then we have a similar thing going on here. The expected value of that sum is just n times the expected value of each thing. And the variance is now n times sigma squared with corresponding standard deviation there. So we'll talk about the sum a little bit less than the average, but sort of similar properties hold there. Okay, so to maybe, okay, so very formally, what we can say here is that in the special case where my random sample is from a normal distribution, so each of my random variables is normal with mean mu and variance sigma squared, then these distributions are for the mean and the sum are also going to be normal. So if and these are also have a normal distribution with sort of those same properties as what we just saw. So the sample mean is going to also be normally distributed with mean mu and variance sigma squared over n, and a similar thing there for the sum. Okay, so just something to point out here. Let me jump back one slide. So this slide here is talking about a random sample from any distribution, right? So here, x1, x2, all the way up to xn could have any distribution. It could be gamma, it could be binomial, it could be whatever. These properties will always hold. This is true regardless. This is always true. But note that here I'm not saying anything about the distribution of the sample mean. So I'm saying that I'm saying what its mean and variance is, but I'm not saying what the distribution is. So here x bar is distributed as something we don't know what it is, but it has mean mu and variance sigma squared over n. So here I'm not saying anything about what the distribution of x bar is. But then going forward a slide, if my individual observations x1 to xn are all normal, then I have sort of this stronger result that the sample mean also has a normal distribution. So a very, very important point. Is that, yeah? Oh, okay, stretching, yeah. Any question? Is that clear? So before I'm saying what the mean and variance is, but I'm not saying anything about the distribution of x bar and t. Here, if I have x1 to xn are normal to start with, then the sampling distributions are also going to be normal. A slightly stronger statement. So here I'm actually saying what the distribution of these things are. Okay. So just to kind of show you this visually, here's a picture on the top of page 13 of your notes. So let's say that I have a random sample, x1 to xn or IID from this normal distribution with mean 35 and variance 16, 4 squared. So the black line down here at the bottom, that's sort of my population distribution, as I'm calling it, the distribution of the individual xi. So x1, x2, they all have a distribution that looks like that black line. But then we go to the blue line, and that's the sampling distribution now of a random sample of size 4. So the key thing is to note that the mean is still the same. The mean of this blue curve is still 35, but the variance is now smaller. It's now 16 over 4. So the blue curve you can see is more squished in than the black curve, right? And then same for the red curve. If I go up to a sample of size 10. The sampling distribution still centered at the mean, still sampled at 35, but now the variance has gotten even smaller, so it's kind of even more squished together. And it's maybe the scale makes it a little hard to see, but the red and the blue lines are exactly a normal distribution. They have that nice bell-shaped curve that sort of tails off on either side. So why are we talking about all this? Well, maybe before I say that, maybe just what you notice about the shape of these distributions. So they're getting more and more squished together, but sort of the overall shape. What do you notice about that? They're all normal distributions, right? So the shape is kind of the same, aside from being more squished together. So the distributions are more closely aligned, but the shape is the same. Okay, so when we start out with a normal, so before when we looked at that gamma example, the shape of my sampling distribution was changing, and here we have this sort of interesting sort of opposite property that when I start with a normal random variable, the shape of my sampling distribution is going to stay the same, although it'll get more and more squished together. Okay, so then we can use these properties to answer questions about the sample mean, just like we did before. So when my x1 to xn are IID normal with mean mu and variance sigma squared, I also know that the sample mean is going to be normal with mean mu and variance sigma squared over n. So now I can say, what if I want to ask a probability question about the sample mean? So the probability that the sample mean is between two numbers, for example, whatever this case may be. Because x bar has a normal distribution, we can do exactly what we've done before. So we'll have, we can standardize this thing, so we can use the table to find probabilities here. We can take a minus the mean divided by the standard deviation, which is now sigma divided by the square root of n. Do the same thing with x bar, subtract its mean divided by the standard deviation. And that's going to give us something involving the standard normal here. So this is a minus mu rewriting this here. And once I have it in this form, this is the z here is distributed as my standard normal, mean 0, variance 1. So if I want to know the probability, for example, that my sample mean is between 30 and 40, then I can do a similar calculation as to what I've done before. Okay, so I'll look through this again, but the obvious question is then what if my original sample is not normal? So what can we do in that case? And that's where we'll get to on Friday. So thank you guys so much for coming, being here today. I do have your homeworks, so come get those, and I will see you guys on Friday. Have a good one.